Good morning, students. Today we are going to discuss Introduction to Dynamic Programming, what dynamic programming is, and what are the different concepts those are present in dynamic programming. Dynamic programming is mainly an optimization over plain recursion. So instead of using recursion or the exponential form of any program, what we can do is we can use a dynamic program which will give us a linear approach to solve the same problem instead of using it or executing the same subcode multiple times. So some recursive algorithms are very inefficient because they solve the same subproblem multiple times. Instead of that, dynamic programming is the best approach for it. Now, what is a weighted balance binary tree is? It's a binary tree which is balanced depending upon the knowledge of the probabilities of searching for each individual node. Now, the example which I have given over here is I have some nodes present, and depending on those nodes, I need to find out that what is the probability that each node will be found in a given tree. You can see that each and every node has given with some weight. That weight is 20, 17, 18, 12, 9, 3 and so on. So 20 is the probability that I'll find G 20 times in my given balance tree. The same way, A will be found 17 times, N will be found 18 times, and so on. Optimal binary search tree. Now, what is optimal binary search tree? It's a binary search tree for which nodes are arranged on levels such that tree cost is minimum. So I have to arrange each and every node on different levels such that the cost which is coming out of my tree should be minimum or should be optimal. Now, for the purpose of better presentation, what we have to do is we can use or we can consider extended BST. Now, what extended BST is, as we have already discussed, extended BST is nothing but a BST. If some nodes are missing in a tree, then I have to add some extra nodes or the fake nodes to it so that I'll be able to balance it, which is called as extended binary search tree. So this example is an example of a binary tree where I'm going to add some nodes at k1, I'm going to add some nodes at k3, at k5, so that it will become what? An extended BST or the balance tree of mine. Now the next part which we are going to see is how we can find out different trees from given keys. Now in this example, what we have done, 10, 20 and 30 are the three keys those are available, from which what I have to do is I have to generate some trees out of it. Now how many trees can be possible? If I am considering 10, 20 and 30 as different roots, then how many combinations can be available for each one of them? So for 10 I have two combinations, for 20 I have only one combination, for 30 I have two different combinations. Now as we are talking about binary search trees, definitely we are going to compare the key value with the root node of mine. Now in first example on tree number 1 and 2, what I can do is I am going to compare 20 and 30 with 10, as 10 is the root of mine. So the first combination which can be generated something like 10, 20 on the right hand side of it, and 30 has to be on the right hand side of my 20 as 30 is greater than 20. Now in second tree, what I can do is 10 is a root, then 30 is on the right hand side of my 10, then definitely as 20 is lesser than 30 and greater than 10, so it has to be on the right hand side of 10 but on the left hand side of 30. So this is the second combination of mine. Then third combination will be 20 as a root, 10 will be on the left hand side, 30 on the right hand side of mine, correct? So this is the only combination available for 4, 30, 10, 20, 30, 20, 10. as we already know that what binary search tree is, so everything has to be compared with the root node of mine. So accordingly I'm going to put all those elements in their right places. So how many number of comparisons are required? Now depending on that, I should know that how many different combinations are required for, sorry, comparisons are required for finding an element. So how that can be found? I can found that for finding 10 in case number 1 I need only one comparison. For finding 2 I need two comparisons. For finding 3 I need three comparisons. In second case, in second tree, for finding 10 I need one comparison. For 30 I need two comparisons. For 20 I need three comparisons, and so on. So the total number of comparisons required to find an element in tree number 1 can be something like 1 plus 2 plus 3. Now 1 is for finding 1, sorry, finding 10, 2 is for finding 20, 3 is for finding 30, divided by number of key elements present in my tree. So 3 are the number of elements present. 1 plus 2 plus 3, that is 6 divided by 3. So 2 is the cost of my tree. Similarly, for number 2 it will be 2. For 3 it will be 1 plus 2 plus 2, 5 by 3. For number 4 it will be 6 by 3. For number 5 again it will be 6 by 3. So the optimal cost which I can find out of these 5 trees are 5 by 3. So 5 by 3 is the optimal cost of mine, where I required minimal efforts to find out what the elements from my tree. Now next, try to consider the dynamic approach for solving the problem. Now how dynamic approach can be used? Now let's see how dynamic approach can be used. Now say for example what I have is, I have 20, 10, 20, 10, 20, 30 and 40 are the 4 keys. Those are available with their frequencies. So keys are 4 and frequencies are 4. So 10 can be found 4 times in given tree, 20 can be found 2 times, 30 can be found 6 times, and 40 can be found 3 times. Now there is a difference between the frequencies of occurrences of my keys and the number of comparisons those are required to find the number of keys. Now as it was a tedious job for performing this operation in recursive way, instead of that what I can do is I can use a dynamic approach to find out what the solution for it. So what will be the solution? Solution is definitely depends on how optimal cost you can find, with the help of which you will come to know that how many comparisons are required to find an element from a tree. So for that purpose what I have to do, I have 4 number of keys, so I have to create a matrix of 5 by 5. Now why 5 by 5? Because my keys are starting from 1, 2, 3, 4. So I have to consider 0, which will fit in my formula. Now formula, we'll see what formula is. Formula will be there in my next slide, where I'll tell you that why 0 is required. 0 is required just because you can see W of 0 comma 4 is equal to summation of I is equal to 1 to 4 f of I. This is the formula which we are going to use, right? And why I have considered 0? Because there is no need to consider it, there is no need to add it to my actual summation values. So it will be very much helpful for me to add 0 to it, because it is present in my formula, but I am not actually adding it to the final summation of mine. In final summation I am going to consider only keys from 1 to 4, not from 0 to 4, but I have to consider keys from 0 to 4 in my weights. So all weights those are present for key 0 are definitely 0, definitely 0. So all the diagonal values are 0. Now we'll try to see that how diagonal values can be 0. So if I am considering this, you can see that the cost of 0 comma 0 can be calculated something like L is equal to j minus I is equal to 0. What is 0? 0 is nothing but the key of mine. So what will give me value 0? So j, I am considering all rows as, all columns as j and all rows as I. So by subtracting the value of I from j, where I can find 0, I can find 0 something like 0 comma 0 will be 0, 1 comma 1 will be 0. That is what 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0, and 4 minus 4 is 0. That's why all diagonal values of mine are zeros. All diagonal values are zeros. So this is how I'll be able to what? Find out the diagonal values of mine. Now what is the next part? Next part is I need to find out their cost. How I can find out their cost? I can find out their cost by using some formula to it. Correct? So check out. The first value which I found out are 0 0 0, 1 1 0, 2 2 0, 3 3 0, 4 4 0. Next which I want to find out is 0 comma 1, then 1 comma 2, then 2 comma 3, and then 3 comma 4, right? So next value should be L is equal to j minus I, which is equal to 1. What is 1? That is key 1. It is key 1. So 1 key has to be considered. So which will give me value 1? So 1 minus 0 will give me value 1. Definitely 1 minus 0 will give me value 1. 2 minus 1 will give me 1. 3 minus 2 will give me 1. 4 minus 3 will give me 1, and that's why I am going to find out the values of 0 1, or I should say 1 0, 2 1, next 3 2, and next 4 3. How to find it out? See, cost of 0 comma 1 is equal to 4, right? Now why it is equal to 4? Just because whenever I am going to find out the values, I have to ignore the first value of mine. What is my first value? First key is 0. I have to ignore 0, right? So what is the first key of mine? First key is 10. Now 1 comma 2, in cost of 1 comma 2 I have to ignore first value. So first key is what? 10. I have to ignore 10. So second is 20. I have to ignore 2. So third is 30. I have to ignore 3. So 4 is 40. Accordingly, the cost of them are 4, 2, 6 and 3. As you can see, the frequencies are 4, 2, 6, 3. So I can directly write down these frequencies over here in the column 0, 1, 1, 2, 2, 3, 3, 4. As 4, 4 is 0, so we are not supposed to write anything into it. So 4, 2, 6, 3 are nothing but the optimal values for column 0, 1, 1, 2, 2, 3 and 3, 4. So which I have already written over there. Now next part is key number 2. Now what I want to do is I want to find out a key which will give me value 2. So which one can give me value 2? It will be something like L is equal to j minus I is equal to 2. So which keys are present in my tree which will give me 2 values? So 2 minus 0 will give me 2, 3 minus 1 will give me 2, and 4 minus 2 will give me 2. So 2 minus 0 is nothing but 0 comma 2, 3 minus 1 is nothing but 1 comma 3, and 4 minus 2 is nothing but 2 comma 4. So what I want to find out now? 0 2, then 1 3 and 2 4. So these are the 3 diagonal values which I need to find out. Now how to find them out? As I told you, we are starting with 0 2, correct? When we are saying 0 2, what we have to do is we have to consider 2 keys only. Now by ignoring the first key, that is 0th key, the remaining 2 keys are first and second. So first key is 10, second key is 20. Now the frequency which is available for occurrence of 10 is 4, and frequency available for 20 is 2. You can see that. Now what I have to do is I have to generate a key by considering 10 and 20 as root nodes of mine. Now if I'm considering 10 and 20 as root nodes, I can be able to generate only two keys. One is 10 as a root, 20 will be on the right hand side of it. Second is 20 as a root and 10 will be on the right hand side of it. Then you can see that one is what? One is number of comparisons those are required to find 10, and two are the comparisons required for 20. One is comparison for finding 20 and two are the comparisons for finding 10. Then what are the keys related to it? For finding 1, 4 is a frequency. For finding 10, 4 is a frequency. Finding 20, 2 is a frequency. So 4 into 1 or 2 into 2, what will become? 4 plus 4, it will become 8. Now 2 into 1 plus 2 into 4, it will become 8 plus 2, 10. So which is the minimum value out of it? Definitely 8 is the minimum. And what is the root of 8? The root of 8 is 1. So what I have written, 0 comma 2, the value for 0 comma 2 is 8 with root 1, which I have written over there. You can see that. Now next is cost of 1 comma 3. The second key which is available was 1 comma 3. Now in 1 comma 3, what I have to do is I have to ignore 1, means key number 1, and I have to consider remaining two keys, means 2 and 3. So 2 is 20 and third key is 30. So 2 is the frequency of it and 6 is the frequency of it. Similarly, if I am considering 20 and 30 are the roots of mine, then I can generate two trees out of it. 20 is a root, 30 will be on the right hand side of 20, 30 as a root and 20 will be on the left hand side of it. The comparisons required to find 20 is 1, comparisons required to find 31, comparisons required to find 32, comparisons required to find 22. So it will become 2 into 1 plus 3 into 6 into 2, sorry, which will become 12 plus 2, 14. Now this will become 6 into 1 and 2 into 2, means 6 plus 4, it will become 10. So which is the lesser one? Definitely 10 is the lesser one with root 30, that is 3, correct? So what I have done, again I have written 10 as a value of it with root 3 and so on. So we have to find values accordingly. Then we'll find values for the remaining table also, and this is the final table which is generated after finding each and every value of my column. So what is the optimal tree I can generate out of this is, definitely I can use root as r of 0 comma 4, which is equal to 3. So 3 is a root of mine, 1 is less than 3, so it will be on the left hand side of it. 4 is greater than 3, it will be on the right hand side of it. Then 0 will be on the left hand side of 1, 2 will be on the right hand side of 1. Then as 4 is on the right hand side, 3 will be on the left hand side of 4 and 4 is on the right hand side of 4, as it is equal and greater than, equal or greater than. So thank you very much. This is all about using dynamic programming for solving the problem of optimal binary tree, OBST. Thank you so much.